In this class, we will begin to talk about inferential statistics, or how we use statistics to make decisions or inferences about populations based upon what we observe in samples. This class will bring together elements we have been discussing, such as the concept of determining that an event is of low probability or unusual. The primary way we make inferences about populations based upon what we observe in samples is through hypothesis testing. Hypothesis testing begins with a research hypothesis, which we will symbolize as H sub 1. We defined the research hypothesis earlier in the course as a statement of the expected difference between groups, or the relationship between variables we expect to observe when we conduct an experiment within certain parameters. But rather than test the hypothesis, we actually test the opposite of the hypothesis, or what we call the null hypothesis, which is represented with the symbol H sub 0. The null hypothesis is the working hypothesis of a study, in which the expected hypothesized difference between the means of groups, or the expected hypothesized relationship or correlation between variables, is said not to exist. This approach to hypothesis testing relies on the notion that we cannot prove anything true, but we can prove the opposite false. As we have seen with the theoretical normal distribution, the curve never touches the x-axis, meaning that even when we have highly unusual events of minuscule probability, there is also always the possibility of events beyond that occurring. Thus, if we find that means between groups are different, as we have hypothesized in a sample, we'll not be able to say with absolute certainty that there will never be no difference between the groups. To do that, we would ultimately desample all members of the population. Thus, we cannot prove our hypotheses based upon what we see in samples. But what we can say is that the opposite of our research hypothesis is not true. If we are able to demonstrate that the null hypothesis is not true, then we have increased the chance of saying that our research hypothesis is true. Thus, when the null is rejected, the researcher makes an argument that the null was rejected because the research hypothesis is liable to be the case and should be accepted. The other important thing about the null is that it is expressed in terms of population parameters, or that it makes a statement about the population. Thus, we might say that the mean of the experimental and control groups are equal in the population, or that there is no correlation between variables in the population. Thus, once again, we're making a decision about what we believe to be the case in the population based upon what we observe in the sample. So how do we come to reject the null hypothesis? To reject the null, we need to establish that the probability for a finding contrary to the null is unusual, or of very low probability. That is to say that the probability is less than 0.05. If we can say that the finding is unusual, then we can assert that it is not due to chance alone, or due to what we say is sampling error. So the question is, how do we determine the probability for a test statistic, and how do we determine what sampling error is? In hypothesis testing, we determine the probability of events by consulting various sampling distributions. Sampling distributions are mathematical or theoretical models that represent distributions of sample statistics if one were to draw infinite samples. These distributions are probability distributions, and we have already looked at two sampling distributions when we discussed the standardized normal distribution and the binomial distribution. Thus, we will use the sampling distributions to determine the probability of obtaining a test statistic of a particular value or greater. Besides Z, the sampling distributions we'll study in this class are the chi-square, T, and F. In order to make inferences about the population, we need to be able to argue that a finding with a sample isn't a one-time thing, or that it isn't due to the fact that we have a very unusual sample. Thus, we need to assess sampling error, which is the degree to which a sample deviates from the population. Thus, we need to determine the extent to which what we observe in this sample is what we would observe in most samples. So can we rule out that this finding is not just due to the luck of the draw? Let's use an example to demonstrate what I mean. Let's say you and I played a 5-card poker game in which I deal 5 cards to each of us, and then we turn over the cards and the high hand wins. Let's deal the first hand, which we can think of as a sample, and let's say you win the first hand. Then we deal another hand, and so forth, and each time determine a winner. If the cards are shuffled and the dealer is fair over infinite samples, there would be rough equivalence in the number of hands won by each of us. Thus, winning any one hand or a finding contrary to the null cannot be considered an unusual event unless it can be found to occur in excess of what could be expected by chance alone or by the luck of the draw. Thus, if after an infinite number of poker hands I was the clear winner, say I won 80% of the hands, you might suspect that something other than chance or the luck of the draw was responsible for dealing the cards. But I hope, parenthetically, you are not thinking that your teacher might be cheating. Perish the thought. Thus, you might conclude that something systematic was going on rather than something random or something that was governed by chance. So in order to determine that a finding is unusual and then cause us to reject the null hypothesis, we have to be able to conclude that what we observe in a sample exemplifies a systematic and non-random trend and did not occur due to chance or merely to the luck of the draw. By systematic, I mean that if we got another sample and then another sample and then another sample and so on, we would continue to find the same thing. Say that the mean of the experimental group was always higher than the mean of the control group. But we are not able to base our decisions on multiple samples. We need to have some way to make a decision based on one sample. So each of our statistics that we'll study have ways to estimate random error or sampling error. In fact, we will learn that the denominator of our test statistics estimates sampling error. So the test statistic that we use to judge against a critical value has been adjusted to estimate sampling error.